Hello and welcome to video lesson 8 on thermal stress and strain. The learning objectives here are to define thermal strain and to explain when thermal stresses can arise in a member. So for these problems, you should read Beer and Johnston section 2.3. So thermal strain happens when a member is unrestrained and it's subjected to a change in temperature. So thermal strains are a result of thermal deformations. And from our previous coursework in physics, we learned that the temperature expansion or contraction of material is given to us by the equation that says delta thermal is equal to alpha, which is the coefficient of thermal expansion, times the length of the member, times the change in temperature. And for strains, the definition would be the change in length over the original length. So when we do apply that formula, we would put the expression for delta thermal up top. We would have the original length in the bottom, those cancel, and the thermal strain for an unrestrained member is alpha delta T. Now keep in mind that for a member to actually experience that strain, it has to be unrestrained. It has to be free to expand or contract. However, we can end up in a lot of trouble in structural design if we have members confined and we have significant thermal loadings and thermal stresses develop when the member is constrained. Such applications can happen in or in concrete slabs where they would be hot from the curing process, perhaps especially hot on a hot day if the concrete was placed on a very hot day. And then you come to a point where there's a very cold night in the middle of winter, and all of a sudden, the slab that wants to be one particular length undergoes a major temperature drop, but that slab might be restrained under its own self weight, and you will see a lot of cracking in slabs as a result of temperature. So that's one practical case where that occurs. So let's take a look at an example. I've got a bar that's 100 inches long, and I know that the coefficient of thermal expansion alpha is 10 to the negative sixth per degree Fahrenheit. And I'd like to know what the change in length is and what the thermal strain is for a 100-degree Fahrenheit temperature increase and a 50-degree Fahrenheit temperature decrease. So keep in mind, we do have a restraint at one end, but other than that, the bar is free to expand or contract. So we have an unrestrained case. For it to be a restrained case, we would need a support over at the free end. And in that case, we would start to develop thermal stresses. So for the first case, I'm asked for the thermal deformation. And to do that, I'm going to need to use the equation that says that the thermal deformation is equal to alpha times L times delta T. Alpha is 10 to the negative sixth per degree Fahrenheit. The original length is 100 inches. And the change in temperature is 100 degrees Fahrenheit. So that gives us a deformation of 0.01 inches. So for epsilon thermal, we would have delta thermal over L, and that would be 0.010 inches divided by 100 inches, or a final thermal strain of 0.00010. And that's a positive because if I heat the temperature, if I heat the bar up, it will expand and the bar will lengthen. For the second case, I have a temperature decrease, which means the bar will want to shrink. So for the thermal deformation, I would still apply alpha times L times delta T to calculate the thermal stress, or the thermal deformation. The thermal deformation would then be 10 to the negative 6th per degree Fahrenheit for alpha times 100 inches for the original length times negative 50 degrees Fahrenheit or negative 0.005 inches. Then for the strain, the thermal strain, we would have that given to us as alpha delta T. That would be 10 to the negative 6th per degree Fahrenheit times negative 50 degrees Fahrenheit. And that would give us 5 times 10 to the negative 5th power for the strain. So once again, strain comes out in unitless dimension. The deformations come out in units of length. So they stay dimensionally consistent. That's it for lesson 8.